of like shifted towards majority of my research nowadays shifted from learning for robotic hands necessarily, but like also to include learning from human data. And today I want to talk about two of my recent work. The first one is how can we learn policies from human demonstrations, egocentric and wild human demonstrations. And the second part is how can we actually design and use humanoid robot hands such that this human data, like this like embodiment gap, morphology gap, is as close as possible. So we can maybe get this started. Yeah, so like as we all know, this is me. This is my colleague at Meta. This is my internship at. This is my work, by the way, that was published in Meta. So as we all know, in the wild, human demonstrations can be collected by anyone, anywhere, with arbitrary backgrounds, which is why we like it because it's very easy to collect. But it is pretty hard to like it is pretty difficult to learn robot policies from it due to the lack of annotations that we can get from human data. Like, let's say that, if we take if we have great annotations that we can get from human data, let's say that we have even meshes of the objects, like perfect simulation of the environment, then learning policies from it would be trivial. But if we have zero annotations from the environment, if we just have RGB video, then it becomes harder and harder to actually learn, robot policies. Um, but yeah, like in this work, with help of RA2 glasses, we were able to actually get pretty accurate annotations that can be used to learn, to learn in the wild, like demonstrations, like to learn policies that is only using human data. And yeah, so like this is the overall framework. Aina learns multi-fingered policies from in the wild human demonstrations collected with RA2 glasses. So this is the first paper that ever used RA2 glasses for policy learning. So like these glasses, they're pretty compact, they are foldable, they're very light. They have high resolution RGB camera on the top left corner, and they have onboard and also like cloud hand pose estimation, and they have slam cameras that are designed in a way that actually allows stereo depth estimation. The major difference between Arya 1 and Arya 2 glasses is this like redesign of the SLAM cameras. If folks like uses Arya 2, I'm not sure like if y'all are using Arya 2, but like this has been the major difference between Arya 1 and Arya 2. Arya 1 glasses have two SLAM cameras like on the corners that are like sort of spread out, whereas Arya 2 glasses have four SLAM cameras. The top, like the front SLAM cameras are like moved more closer to each other now, and the right and left SLAM cameras like looking upward outside more. So by using the front SLAM frames, we are actually able to get a pretty good metric depth using foundation stereo or any sort of depth like stereo depth estimation framework. Sorry, two glasses. INA consists of three key steps. The first one is in the wild human data collection with ARIA Gen 2. The second one is in scene data collection. And the third one is policy learning by using these two data modalities. So it is like, as I was doing this, I actually didn't really, as I was like developing this framework, I actually didn't really think about like the, third person, like in scene data collection as, I mean, I didn't necessarily frame it in my mind as exocentric, but it is like somewhat like here I'm sort of using like egocentric data to generalize and exocentric data to sort of ground my demonstrations. The most important use of this in scene data collection is to ground and move all of the in the wild demonstrations to the same space as the robots' environment. And in that way, once we move all of the demonstrations to the same place, the same coordinate frame as robots, then we can train policies with it. And the way to go with it is like here's the processing part. So with this demonstration, we just like on RGB side, we segment out the objects with grounded segmentation, and then we track them using code tracker. And then on the 3D part, by using these SLAM cameras, we rectify those SLAM cameras, SLAM frames, and then we input that to Foundation Stereo, and Foundation Stereo gives pretty good depth estimates given properly rectified SLAM cameras. And then so this is the depth that we can get from Foundation Pose. And if you just and then we just um we basically just like unproject this 2D tracked points to this 3D information to get 3D object points aligned with the hand information.
Sorry, I had a question.
Yeah.
Uh, you said, can you repeat what is the use? So you said you have some exocentric view data and some egocentric view data. Is that correct?
So like I have a single demonstration of sorry. Yeah, I have like, so this is the egocentric demonstration that I'm referring to. This, we have for this task, like for cup pouring task, we have like, we just go out and then collect a bunch of demonstrations in the wild. And then we collect a single demonstration in the same scene as the robots is. So this is like the environment that robot is like, working on. Like yeah, like yeah, it's not from this view but from the other view. This is where the robot executes all of its actions. And this environment uses real sense cameras to get the object point clouds, because at the time RES streaming was not working. Were not able to stream with RE glasses, so we were using RGB cameras, two RGB cameras surrounding this environment in a calibrated, with hand-eye calibration done. So we collect also one demonstration in this environment. So that's the exocentric data.
Okay, thank you.
Yeah, yeah.
I'm sorry, just follow up to that question. You also talked about code training. After that, do you also then collect some robot data that you train with? Or
No.
so okay. So what does the code training exactly mean there?
Yeah, co-training is that exocentric data and the egocentric data.
See, okay.
Yeah, yeah.
So one demonstration of exo, and in this particular task, one demonstration of exo and how many of the in the wild ego data?
50 demonstrations.
Okay.
Sorry, actually, just to repeat, so for I didn't completely understand why you need exocentric still. Is it because you said there was some streaming issue, or is there a reason for having exocentric? Because you could have collected in the wild egocentric as well, right?
Yes. So like the so egocentric data is kind of like an interesting modality because like as you collect it, first your head moves as well. Your head moves when you move, like when you collect the demonstration, and
Yeah.
also you're pretty limited by the height, like the distance between your eye and the observation space. So like, collecting all of your demonstrations with respect to the RGB frame, that's why it was not really like working well. Because like even when I was looking at it qualitatively, a demonstration that I collected from like like RGB glasses, for example, they have like, you know, um, with respect to the height of the operation space that I'm at, the points that I would get would have like this like tilts to them almost. And like they all had different tilts to them. If I'm like operating in different like yeah, like different heights, with different like, like arm length and etc., the observations that I would get actually will be pretty different.
Okay.
So that's why like I didn't want to, and also like to remove this like tilt from the data as well. Like all of the data demonstrations that I would have like would be like tilted. So actually, I'm just realizing that I forgot to sort of motivate something. So if you were to like save everything with respect to the RGB, right? And then during deployment time, we have all these points with respect to RGB frame, like in this area. And during deployment time, we would shift this RGB to a point where a robot would operate, right? Like in order to have some some similar distribution between the training and the deployment environment, we would need to somehow shift these like points that we collected in the wild to the robots scene. So this demonstration is used to properly extract that information. One, I mean, one argument is, of course, like if you have large enough data, then like this distribution will be covered. Like if you have like hundreds and hundreds of demonstrations, this distribution will be covered, which is like the case while why we have human demonstrations and et cetera, which I understand. But I think like, in this setup of like in this setup, 50 demonstrations, like one, like with 50 demonstrations, that shift, you know, adding naive augmentations, for example, was not enough to move that distribution in a meaningful and workful way. So that's why we need to shift those points to the robots scene. And in order to properly shift those robots scene, I used like an extra in-scene data collection. But, like there are like a lot of different works that actually handles this problem in different ways. Like for example, Zero Mimic, they just like they just measured the RGB from the camera to the middle of the operation space and then basically like use that to shift all of the environments. Sorry, Zero Mimic assumes some like set difference between the camera and the operation space. Like Ego Zero uses Oracle Marker. Like I don't know, like different frameworks without framing it this way, but they actually do like these sort of tricks to make sure the operation space like is some set amount of distance from the camera to like this is my interpretation, at least like from the literature.
Got it. Thank you.
Yeah. Um, yeah, so like once we have these 3D points, we use that in scene demonstrations to align. And then once everything in the environment that we have is aligned and in the same space as the robots is, we can do policy learning on these 3D points. So given an observation horizon that looks like this, we extract each point like point horizon. So like each of these points, like each of these lines, dribble lines, they represent a history of points. So like we treat each of these points as a token, as a separate token. So we pass them, like we flatten each of these points using a vector neuron MLP. And then we have these like tokens per point. And we want to input them to a transformer encoder. But since the object points are not correlated from one demonstration to another, because it depends on how the segmentation was done, like like the top corner of a cup is not the top corner of a cup at a different demonstration. Like the ith point might be top corner of a cup in one demonstration, but it's not the same for another demonstration. So that's why like these these red points as positions change from demo to demo. So that's why we only include positional embedding for the hand points. And then we pass them through an encoder. Then I mean we pass them like and then we pass the output of the encoder through an MLP. Then we just supervise this whole thing with the MSE loss between the predicted hand points and the actual hand points. And then yeah, we just like end-to-end train this whole system in this way. It is a relatively small model. It's around like 11 million parameters. It's pretty small and it would train very quickly. Like I guess yeah, this is like the like I think making everything point is has like both advantages and disadvantages that comes with it. Like the model ends up being very like small, very light. It learns like it does like it is very easy to augment points. You can just augment like every like points in a lot of different ways, which makes it easy to during deployment time. Like you can do a lot of like tricks around points to make it work. Um, but it also comes with like negatives as well because it now like relies a lot on the way you track the points and relying on point tracking has its own negatives as well. Um, but yeah. So yeah, like and in this way we were able to learn policies from these in the wild demonstrations. Oh, and it also making everything point, which was why the reason why I made that annotation motivation sort of like if you have good enough annotations, it becomes easier to train policies. But if you don't have like good enough annotations, then like it becomes harder and harder to train policies. But yeah, like it also closes the visual difference. Now, like when we extract all the annotations, like it's just points which can be used for robot deployment as well. But yeah, so we were able to like train policies with all of these different backgrounds, all of these different spaces, heights, and everything. And here is the um, policy deployment. This is like the stowing task. It picks up the ball and closes the lid. Yeah, and then yeah. Then this is the example of wiping task. So for this wiping task, the demonstrations are collected like this, like this. So like the and it's also all in point based. So we don't really condition where to wipe exactly, but it's just the success rate was sort of calculated on how good the grasp is, how well it actually is able to wipe, um, but not whether it's going towards the wipe. So the wipe is just like drawn very randomly. And then we have this like simple toy picking task. Then the saucer press, that is, we have liner reorientation, and then this task. This was a very difficult task for this framework to learn. It's oven turning. Yeah.
Or I have a question.
Yeah.
So you mentioned that for the observation, you actually get the points with steps from the observation, right? So how do you sample the points from the detected objects? Actually,
We use SEM like a SEM. So there's like this like grounded SEM like a repo that basically uses Dino features. So like it inputs like a text, it inputs like text description, and then it uses Dino features and SAM to like it uses first SAM to segment all of the objects, and then gets the Dino features of um clip features of the language, the words that are inputted, and then just uses some similarity metric to get the segmentations that are for that language annotation. So we first get object segments, like object masks, using this like grounded sim. Then we track these points, track this segmentation using co-tracker.
okay. How do you decide the points number, the tracking points number?
I used 500. I just set it to be 500. Like because all of them are inputted as separate tokens, I didn't want to like make it too large. And 500, like I was like it seemed like a accurate amount of points. Like it was not like it wasn't too little such that like on during tracking like the huge bulk of the object would not be tracked or anything like that. So like yeah, I used 500.
So if let's assume a task like bimanual manipulation task, and if you have a very large object or multiple objects to manipulate, I think that then the points number is kind of tricky, right? The decision. Yeah. Do you have any thoughts on that about?
I see. I mean, like, I guess, yeah, that is a little bit tricky. Maybe you could potentially use like the sizes of the objects as like a weight to sample how many points you want. Like if it's like this, if it's like a single gigantic object,
Mhm.
you don't really need a lot of points to track it. But if it's like a smaller object, you need a lot of tracks like to track on it. And if you use like SAM, for example, SAM 2D inputs this grid size when you're like asking it to, give you segmentation. And if you increase that grid size, like grid size is like how do you split, like how densely or how sparsely do you split your image into points? Like that's what grid size is. So if it's one, it's very dense. It's all pixels are points. And if it's five, it's like, once in five pixels are just points. So if you, let's say that you could potentially just use SAM, like SAM 2 or SAM 3D, sorry, SAM, yeah, whichever the SAMs, to like with very low grid size, like so you can get like very dense masks. But for larger objects, like pixel wise, you can maybe compare this. For larger objects, you can just sample like less points from that segmentation, whereas for smaller objects, you can sample more points. But I think like on average, like as a metric, you would definitely need around, I want to say like 50 or 100 points per object. I would want to say.
Okay.
Also, a question. So your policy predicts uh, uh, the action space is basically the position of those points, and
Position
you
of the hand points.
position of the. Sorry, is it hand pose or is it position of these fingertip points?
Hi, position of the fingertip points, but not the object points, is what I meant.
I see, I see. And so, given the position of the fingertip points, then you perform some kind of IK to get the robot joints. There's no hand, like end effector 6-off pose involved in this, right?
Yeah, no, the IK that I implemented is like a whole body IK. So it inputs the fingertips and it calculates the joints for both hand and arm.
Okay, got it.
Yeah, like one of the limitations that I ran into here, like I think this is pretty important during the deployment. Like as humans, we collect a lot of demonstrations like with our wrists. Like so like all of our like interactions are like this, like this and etc. Whereas all the tabletops like manipulators are usually like mounted like this because this is very hard to, this is very hard for a manipulator to do because usually this part hits the table if you don't have like a wrist that is like specific, which majority of the tabletop manipulators do not. So if you do like first get the wrist and then move the end effector to the wrist and then do hand IK, that doesn't work for a lot of cases. So that's why like I strongly suggest like for folks who are working on these sort of things, it's really I think important to do a full body IK. Yeah,
Got it. Thanks.
because like yeah, sure. Like yeah, like for this case, for example, I mean, I guess like this is also like a very like I mean, like even humans is like positions are very weird here, but in any of these tasks, like even in this like very simple task, because the human hand actually comes from like we don't come like this to the like toaster. We usually come like this to the toaster. Like we go from the bottom and then go up. Whereas like if you do wrist and then finger, it becomes much harder to do that. Whereas this is very easy. And I mean it's not easy or hard actually. It just hits the ground. It's the table or not. So yeah. Yeah, so then and then we sort of evaluated on how important the different types of data used in INA. So we try to learn policies with in the wild only, in scene only. So, like a one thing before getting to that, this in-scene demonstration that we have is used for both aligning the domains of in the wild and the robot environment, but also it helps with the training points as well, like sort of shifting the distribution of the in the wild points to the training scene points. Um, the reason why I like my explanation of how it helps during training is because the observation that we get from real sense cameras, like two real sense cameras in a calibrated environment, is slightly different than the observation that we get from in scene demonstrations. Because with like sorry, in the wild demonstrations, because in the wild demonstrations our head moves, we are sort of always limited to a single view point. Whereas with real sense, it is like multi-view. So like it's much more elaborate, like yeah, it's multiple view of point cloud, and my head doesn't move, so the point clouds also doesn't move. So these two reasons also like causes the in-scene demonstration to help with the training as well. So like if you take a look at, for example, here, in the wild only is the light brown. Both of these tasks like fail pretty badly. So here, what I did in the wild in the wild only to align the domains I used what I mentioned before. I got all of the points with respect to the RGB frame, and then I shifted them to the center of operation space by measuring like the distance from the RGB to the center of operation space. And the majority, like, like how it majorly looks like is all of the objects were tilted compared to the actual like observation that we're getting. It's also important to note in the wild, like all of these experiments are done with real sense cameras in the calibrated environment used to extract the points. So this tilting like is kind of important in that sense because we don't have that tilt in the deployment part. Then light pink is in scene only. As you can see, compared to Aina, the generalization is much worse. But for the point where like it is a single point on the, like wherever that object was during in scene demonstration, like it succeeds pretty well. And like also like, like I also add some rotational and translational augmentation during training. So like it also can generalize like a little bit around it, but like it was pretty specific to that object to that location. And then if we add in scene training, so we add in scene, we only use in scene for training, and but we don't use it for domain alignment. Is the purple one, like dark purple one is that. So here I do the domain alignment as I just mentioned with by measuring the RGB and shifting all of the points to the center of the operation space in that way, and then we add in scene to the training. Here we observe like success, like higher success rate for tasks like toaster press, for example, which is relatively simple. So this tilting for this task does not necessarily hurt too much because like with the tilts, like the space, like place of the handle, like does not move significantly, or like like it still like is able to like close, like do like press the toaster. Whereas for toy picking, like it would behave very out of distribution-y, was my experience. And then in scene transforming in the wild is when we don't add in scene to the training, but we only use in scene to transform the data, and then we use in the wild training. This also performed, yeah, like this performed pretty badly, and I think like this is because of the reason why I mentioned how the observations are very different compared to in scene and in the wild. But when we add all of them together, it actually helps with both generalization and like it works. So like yeah, like the way I like in my experiences, the way like from my interpretation of how the robot was moving, um, yeah, my interpretation was that the in-scene data helped a lot with pushing the observations closer to the robot's scene, whereas in the wild helped with generalization more.
Um, Quick question here. Can you give like a sense of the scale of the data sets that you're using with the in scene and the in the wild? Like how many demonstrations for each of the tasks you're using?
It is a 50 demonstration in the wild and one demonstration in scene
Or for both the tasks?
per task.
Okay, got it.
Yeah. Yeah, like and then so like because we were building this, like idea of okay, yeah, like domain alignment should help with different operation spaces. So like what we did is like we experimented on deploying this policy in different operation spaces, and it like seemed to generalize relatively well as well, like like around 6 out of 10, 5 out of 10 success rate for these like different heights. Like what I did, like so what we do is here we again collect a new demonstration per like for these like different heights, and then we just like retrain the whole thing. So we basically whatever we were doing for in domain, like regular, we just collect one more in scene demonstration and everything like like it can just like because everything is domain like aligned with that in scene demonstration, it's just like easy to use different operation heights as well. Is like was the point of this experiment. And then how well does Aina generalize? So these generalizations are heavily dependent on like of course like I mean the points, since everything is point. If the points look different, very different compared to the original object, then it fails. but like the color doesn't really matter. These like small differences between one toaster to another, where the handle is slightly smaller and etc. Like they don't matter as much as expected. But like if the like here, for example, like the robot would behave very, very differently if the object is significantly different. Like it would pick up the object like with this, for example, package bowl, but it would just like yeah, like I would just fail to put it in. And yeah, these failed pretty badly. These two examples. Yeah, so this was I know, dexterity from small lessons. Like I would say, like I think, like from introducing, yeah, like introducing this domain alignment problem, like I don't know, like using Arya glasses and everything. Like I think it was like a good, uh, like I would say, like like it's a yeah, like like those are the things that I introduced. But I also think that it has a lot of limitations. Like I think the biggest limitation that I would say is the lack of force information from human demonstrations, like in general. And I kind of want folks to start thinking about this problem because I feel like it's getting yeah, like I mean, like with lack of this information, we only can go some far in Dexter's manipulation research, I think. Because, for example, with this task, with some of the tasks, yeah, for this task, I needed to like sort of do this heuristic deployment, where if the fingertips were closer to each other than 3 centimeters, I would push the fingertips closer to each other in order for it to pick this ball up, because it would just go there and it would just like go to the ball, but then it wouldn't grab it because visual annotations are not enough. Whereas like I had the similar problem with this cup pouring task as well. Like with this cup pouring task as well, I needed to hard code like, oh, if it goes closer than 5 centimeter, then move the fingertips closer to each other. So first, like there are multiple problems with this. Like the first one is that like it requires some, prior information about the task, right? Like I know what the size of this cup is. I know what task I'm going to do, which hinders the generalization, like, oh, AGI generalization significantly. And also, I mean, like, and it also makes sense. It's like a very, like the problem that we're solving comes with this like limitation automatically because visual annotations, like we're always limited with visual annotations. So like by just using visual annotations, it's really hard to understand how much force I'm applying. Like, yeah, like I mean, when I'm holding this cup, my fingers don't really change when I'm not holding them. So like the robot does not have any information on like, why would move my fingers closer to each other. So I think that's like the major limitation of this framework, which also causes difficulties in learning very dexterous tasks as well. So that's why like the dexterous task that I could make this framework to work was this, which does not, require a lot of force, like not like, very contact heavy information, but it was like it's still like, some source, like some like, some dexterity, but the force to be applied is actually like very minimal. So I think like yeah, like so I think these are very important, and especially with dexterous tasks, force and contact information is pretty valuable. Yeah, so I think that's pretty important, and also reliance on object points, as I said, the tracking sometimes we lose track of tracking. So like that was like that's always like a limitation. Like we can only scale to an extent when we're working with object points. Um, yeah, yeah. And like this scaling is what I'm referring to. Like if you were to work like, yeah, like very large scale, very involved demonstrations, if that's like the goal that we're pushing for, I think object points like is limiting to an extent. Um, yeah. Is there any other questions? If not, I can go to the hand paper. Okay. Yeah, so the second part of the presentation that I want to talk about is the Ruka hand that we released. So, so usually, like in like so we released this paper last year, February, like around February. Around that time, now in the last year, so many hands came up, so many humanoid hands came up. But at that time, I think Sharpa had just come out, and Sharpa is pretty expensive. And but other than that, like none of the like Wuji was not out. I don't know, Tether AI was not out. Like all the, I guess like nowadays, like becoming easier and easier to access humanoid hands were not in the like out yet. And like the majority of the hands that were being used and that are still being used were either they had like very low degrees of freedom, like Inspire, I don't know, like Accent or something like that, like they had only like 6 stops or something, or they were very expensive, or they were very bulky and large. And so in this paper, what we sort of like introduced is an open source humanoid hand that is tendon driven. As you can see, like it has like these ropes that where the control is done on the wrist. It builds only it was only $1,300, but then the like whatever is happening in the world happened. And then like now I think it's actually more expensive. And it took only 7 hours to build. It had 15 degrees of freedom, and it was humanoid, was the overall idea. But as like when we're building a tendon-driven hand, the mapping from joint to fingertip mapping or motor to joint angle mapping becomes slightly non-trivial because like uh, past state of the tendon impacts how the future states of the tendons are going to be. So there is no one-to-one mapping between tendons and fingertips. Um, and also, like it is by nature, it's not really clear. If we assume, for example, linear relation between the joint and the motors, then we can just interpolate linearly. But like this relation is sort of unclear. So in order to tackle this problem, we deployed a learning-based approach. And we attached a mocap, a motion capture glove on the back of the hand. And then we just like randomly iterated, like just like randomly moved the hand around and then collected a self like autonomous data, basically, where we just like save the corresponding fingertip positions and the joint angle positions and these motor positions that we save. And then we train like a sequential model, a very simple like 1 million parameter, very simple LSTM that inputs the past fingertip positions and also the desired like past desired fingertip positions, and then just predicts the motor position to get there. So we train this controller per every finger. Per finger, we train this controller, and then we just supervise this whole thing with MSE loss actions, like MSE loss on the actions. And this actually gave pretty accurate controllers. This would give pretty accurate controllers. This is the sawing task that we had here. We don't really use the controller as much. We just like close it. But the idea was that it was strong enough to actually saw this sponge. Then we had this Nutella task. So these are all teleoperated. But we were able to teleoperate this Nutella and then just take the cap off. Then this screwdriver task in hand rotation sort of was another one. And then insertion of this battery. Overall, like I think like in this paper, both from design perspective, like at the time there weren't that many humanoid hands. So from design perspective, like it was like important to like think about it. But also like I think just like the idea of being able to use a human-like glove on the robots enables us to learn controllers for it as well. Like that was like that was the thought that we wanted to like we sort of learned about this. Um like as long as like we can use a human device on a robot, then we can learn human-like behaviors on the robot as well. Like like was the overall idea. Yeah, this is like a teleoperation that we did. Like we just attached like two arco markers on the Manus gloves and then just like operated with them with the whole hand. And yeah, this was
Oh,
and also,
oh.
yeah.
I mean, so I have tried teleoperating with a kind of a manus glove and a dexterous hand. I realized that it's very difficult to actually like know how what the hand is doing without any haptic feedback. So like I see like the kind of the point you're making about force, and I agree that's very important. But like when I was study operating it, I found it really hard to interpret what the force actually was that the robot was kind of sensing without actually having the same object in my hand, right? Um, I know like that's not the focus of this work, but I was wondering what you think about like haptic feedback and like kind of this dexterous stereo kind of teleop based works. Whether I actually don't know a lot of like related works. Like I'm not up to date with the recent works in this space, so just wondering if there's anything out there already. I don't know.
Yeah, I mean, like I think haptic work, yeah, like there's a lot of push for yeah, like having good haptic feedback. Um, like I think me personally, I'm kind of losing hope on teleoperation for hands. Like I mean, at least like maybe if I'm not losing hope, like it's slowly becoming a problem that is not necessarily like a problem to be solved in research labs. Like I think improving, yes, like I mean haptic feedback will improve teleoperation, but it will still take hours and hours and hours of data to just like, learn a simple task. Which is why like makes me a little bit hopeless about the teleoperation research. Like which is like why it makes me, yeah, yeah. Like I mean I think it's only limited. Like we're only limited by like how much ever good feedback that we're going to get. Like I think like we will always like the teleoperator will always need to have like virtual mapping of what their hand is doing and the robot is doing. Like if the retargeting, yeah, like so I mean, yeah, like I think it's like kind of like a slightly difficult problem to actually like scale if that's what we're caring for. I mean, sure, like I mean, if the scaling is what we care for, I think teleoperation is slowly going to die. But if the dexterity is what we're caring for, like if we're trying to like collect very difficult tasks and then somehow use that one or two demonstrations that are collected like very difficultly as like an anchor to learn, I don't know, more general policies. Like I think that could be one branch where I could see teleoperation research like be very useful. Yeah, but I think like because of this, like, all large data, all scale up, everything, like, that hype, like I feel like teleoperation like research is like slowly yeah, like getting harder and harder to do. But yeah, but like yes, like I mean haptic feedback is definitely like would be a big improvement to the whole system. I think there are good works that are like using haptic feedback. Um yeah, it's kind of hard. It's like with large systems that we built in these research labs, I feel like the larger and bulkier the system gets, the harder it becomes for other people to use. So like and like all the haptic research that are done that I've run into so far, uh, they're very bulky and it requires a lot of work to make it work. So I think like if you're interested in working on something like this, like I would like from a user perspective, I'm most interested in like how easy it is for other people to use. Like I think like yeah, that's what I would say. I guess like I said bunch of stuff as an answer to your question, but I hope yeah.
It's interesting that you said that like you don't believe in like the teleoperation research. So I kind of wanted to know what you actually believe in then. Like, what's the way to go to scale, um, like robot learning, I guess. Yeah.
Yeah, I mean I think like I'm very hopeful from human data.
Mhm.
I have a lot of hopes from it. But yeah, I mean it's like it is I mean like at least like I almost like I'm hopeful for the data that gets automatically generated. Like I feel like but I think like yeah, maybe some amount of robot data we will like, I don't know, use slowly and more and more and more as like the robot data will also become scalable. Like once, like I don't know, like now, for example, like we see 1X, for example, like they supposedly started selling the humanoid robots and we don't know what's happening behind them. Yes, but it is a great way for them to collect large amounts of data. Like if they were to just like sell hundreds of robots like in one day, then they can collect like incredibly like scaling data from robots immediately. So like I think that could be like a good way to collect like large scales of robot data. But I don't know. But I don't know. Like I think this like, a single company just hires a bunch of people and collects like teleoperates non like for hours robots like for hours, and then another company without sharing any data with each other, obviously, like hires again hundreds of people and have them teleoperate for hours, and then another company redoes this all of it over and over again, and because they don't share any data because capitalism, like obviously they're basically redoing everything that they're doing. Like I don't know, like it's like yeah, I feel like it's like like it's only limited by the max of all of theirs is response like efforts, right? Because none of them are gonna open source it as well. So it's just like so it's basically just like a very good company, one very good company doing this thing rather than all of these companies are doing it. So I mean, I don't know, yeah. But these are all just like hot takes, obviously, like with zero like I mean it's just they're just my thoughts. But yeah, like I mean, which is why like I mean I feel like research in academic labs who don't have that amount of money or like uh yeah like time to share, time to give, like I think it's kind of getting limited. Yeah, is my thought.
Thanks for sharing that.
Yeah, sure. Of course.
Yeah, Mark, I also have one more question.
Mhm.
So based on the uh your framework of collecting in the wild data and in the scene data for dexterous manipulation, uh let's assume the in the wild egocentric data is unlimited. Uh, how efficient do you think is the generalization transferability, and what's the what what else limitation do you think still exists for uh, dexterous manipulation?
Hmm. So like I think hmm, right, yeah.
So I think your work in your pipeline, the transferability is already very efficient, like 50 in the wild demo and one in the scene demo, right? Uh,
Hmm.
I think that's impressive. Yeah. Um,
Yeah. Yeah, like I mean I think so like as a response, yeah, like I mean I think that problem of like yeah, X amount of in the wild and one in domain, like I think if you're using points, this is very like it's very easy to do this alignment. And if when you're using points, like especially like this like per token information, um like it's kind of like a very, when you think about it, it's a very simple problem. Like we frame this whole system as a very simple problem. It's just points moving and then you predict again points moving. So we simplify this problem so much more compared to if you were to input image and then predict joint angles. Like the problem formulation is so much difficult there. Like it's so much unclear from the data perspective, from the model perspective. So I think that helps a lot. Like simplifying as like points moving and points, next points moving. The problem, like I think this simplifies the system a lot because it's almost like a world model, like very simplified world model is like what we're sort of like trying to do because everything is in the point space. If we had correlation, it was going to be like exact like world model, like, and we could like predict the future states and etc. But because yeah, whatever. But yeah, like so like I think that helps a lot. But yeah, like as I said, it comes with limitations as well. Like, for example, in from models' perspective, toy picking. Like if I were to put another toy, but that is like much larger, it doesn't have any idea of point, like, like what toy is. It doesn't have any like a higher level planning, like I think like yeah, like a higher level idea of what's happening and what it's actually doing as a task, the model. Like it's just like, predicting, okay, this is the bulk, like this is the motion of points, and I need to do this to, like yeah, this is what happened, and I'm gonna do this as the points like in the future. So it is like its behavior, like I think the generalization capability of this model, like it's a very small model, so it is basically learning how to move the points, which makes it very easy to train. But I think like, if you were to, yeah, like I mean, I think like it doesn't have like larger planning capabilities. Um, so yeah, like I think like yeah, like that's yeah, like I mean, like one could potentially, offload this planning to a separate model like that, like can do this planning, and then like, use these simpler models, like a simpler like learning frameworks to learn these skills, but like, use like a smarter but larger model that is harder to train to do like planning. Like, but in this way, like you can like generalize like 50 to 1. We can keep that light ratio. But yeah, yeah. But yeah, like so, yeah. As a response to your question about what's the limitation for dexterous manipulation, like I think still low level interactions is like a very limited, which actually like could like teleportation could help with this, like having some grounded demonstrations, like grounded robot data, like would help with this because we immediately get it. But yeah, like I think having like this sense of low level interaction from the fingertips is very difficult. Like one of the approaches, like behaviors that I would observe is it was pretty good at generalizing spatially, like when the motion is large, but when the motion is small, like like when the motion is like very small, it would like the model would learn to skip that motion. So I think like sort of learning those yeah, like a low level interactions is also pretty unsolved, I would say.
Okay.
Again,
Okay.
yeah.
Do people online have questions? Okay. Yeah, I think that's all for today. Yeah. Thank
Okay.
you so much for the talk. It's great. Yeah.
Yeah, yeah, of course. Yeah, like nice to meet you all. Nice to meet you all. And yeah, like thank you for having me.
Thank you.
Thank you.
Yeah. Thank you. Have a good day, good week.
Okay.